All right. Hello everyone. Welcome to the Guaranteed Safe AI seminars. I'm Orpheus, founder of Horizon Omega, a nonprofit focused on facilitating AI safety progress. The purpose of these events is to advance the Guaranteed Safe AI research program. It's a research program towards building AI systems with safety guarantees, using world models, safety specs, and verifiers, yielding proofs or probabilistic bounds of behavior. Today, we have the pleasure of hosting Benjamin Plaut, which is a postdoc at Chai studying guaranteed safe AI, with a talk entitled Safe Learning Under Irreversible Dynamics via Asking for Help. So the session is about an hour. Usually we have 30, 40 minutes for presentation. We can have questions during the talk, and the remainder of the time is for discussion. So thank you all for being here. Thank you, Ben, for presenting, and the floor is yours.
Great, thanks so much for that introduction. And yeah, really excited to be here at Guaranteed Safe AI seminar since Guaranteed Safe AI is the primary motivation for my work. So thanks for coming to my talk, Safe Learning Under Irreversible Dynamics via Asking for Help. And this is joint work with Juan Liavano Karim, Hanlin Ju, and Stuart Russell. Here are some takeaways I'd like you to keep in mind during the talk. First, I'm going to argue that misalignment can be framed as misgeneralization, which is sort of not the usual framing, maybe, but I think is useful and instructive. Second, I'm going to talk about how RL theory mostly assumes catastrophe is impossible, which is clearly not true and is specifically not true in the types of applications that I'm most concerned about and maybe that you are concerned about as well. And then our primary theoretical result is we provide, to my knowledge, the first proof that an agent can learn an arbitrary objective while becoming self-sufficient in an unknown and unbounded environment without causing catastrophe or needing to be reset or anything like that. So let's start with that first one, misalignment as misgeneralization. What does this mean? Let's consider a classic setup where a robot is making coffee. And maybe the robot during training was only ever trained on empty counters, and it got really good at making coffee when the counter is empty. But what happens in deployment when there's actually other stuff on the counter? Let's say a vase on the counter. Well, it never learned anything about vases, so it just ignores the vase, which causes it to break. So, what went wrong here? Well, the sort of traditional AI alignment framing would say, no, 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 you trained it with reward function R, but you actually should have trained it with reward function R prime, which gives it points for making coffee, but subtracts 100 points every time it breaks a vase. And while I think this does describe what is happening, there's another framing that I kind of prefer, which is the generalization framing, where we say, actually, R was totally fine up until this point, and it was totally fine in training. The problem is just that there's some ambiguous generalization going on. If the robot has never seen a vase before, it has no way to know whether breaking vases is good or bad or neutral. And in these types of situations, we can often imagine that the agent will kind of default to treating it as neutral, which in this case leads to it breaking the vase. So there's sort of a fundamental issue here with the lack of training data that it just hasn't seen this type of scenario before. Let's talk a little bit more about what this kind of means and the implications of this. If we imagine this standard pipeline where first you train the model and then you deploy it, the key difference in training is that there's a supervisor who is paying attention to the agent and can potentially make adjustments if things go badly. So the best case scenario is the agent does what we want in training, and then we deploy it, and it also does what we want in deployment. Another scenario that's okay is the agent doesn't do what we want in training, And in this situation, the supervisor will hopefully notice that and say, oh, we better not deploy it. Now, the type of scenario that I'm concerned about, or the most concerned about, is where it does what we want in training. So the supervisor says, great, let's go ahead and deploy it, but then it doesn't do what we want in deployment. And now, not only is it harder to supervise, it's also out in the real world where its actions probably have more consequences. So, how would we deal with this problem? One approach is to say, well, let's just supervise it during deployment. But A, this is resource intensive. If there's a lot of these agents going on, then you need a lot of supervisors. And B, even if you're supervising it, it might be hard to catch it before it makes a really bad error. Another approach is to say, well, let's just not have generalization at all. Let's just make sure that the training distribution matches the deployment distribution. But this is going to be really hard for general environments. And the real world in particular is always changing. So it's fully possible that the agent will encounter a scenario during deployment that just didn't exist at all during training. You might also say, I actually really like that traditional alignment framing, and actually, I'm just going to write down the perfect reward function that handles every possible scenario, including the vase breaking, including everything else. And I would say, even if you have that reward function, if we think about a standard gradient descent style or similar to that algorithm, the agent will only make the relevant gradient updates if it sees the relevant training examples. So even if your reward function captures that, if it doesn't actually see a vase in training, it won't make the relevant gradient updates. So I'm not trying to argue here that all of these approaches are bad. I think these are all worth working on, and there is research on all of these. I'm just arguing that none of them solve the problem, and I favor a slightly different approach, which is trying to train agents to recognize when they're uncertain or in an unfamiliar scenario, and then be cautious. And in this talk, we're going to think of being cautious primarily as asking for help. Okay, so we're going to work in an MDP setting, which you may be familiar with, where the agent observes some state. It's going to take some action. The environment then provides a reward based on the state and the action, and also provides the next state. So we're also going to be doing online learning where the agent only gets one chance. There's also online learning with multiple episodes, but here we're trying to model deployment in the real world where you let this agent out there, it starts doing stuff, and all of the actions it takes are going to actually have impacts on the real world. You can't say, well, yeah, I deployed it and then it did lots of bad stuff, but that was actually just the first episode. Now we're going to deploy it again, and then with enough episodes, it's okay. The agent only gets one chance. A lot of existing RL algorithms, including both the offline and online settings, basically learn through trial and error. So they try some action and they see if it goes well, and if it does, maybe they do it again. If it doesn't, maybe they do something else. And, with enough time, they can figure out what types of actions are going to lead to a higher reward and stuff, as long as they don't make any irreversible mistakes along the way. And this talk is about MDPs with irreversible dynamics, like it says in the title. So let's just look at a simple MDP like this. There's some start state, and if it takes action A, it'll go to heaven where it gets perfect reward forever. And if it takes action A prime, it'll go to hell where it gets terrible reward forever. Now, what's going to happen if you do trial and error here? Well, maybe you guess randomly on the first step, and there's a 50% chance that you go to heaven, and there's a 50% chance that you go to hell. And once you go to hell, it's over. Now, I don't think we want AI systems in high stakes situations out there in the world saying, well, I'm just going to guess randomly. There's a 50% chance I get it. So when you start to introduce these irreversible dynamics, the trial and error approach starts to not look as appealing. How does RL theory deal with this? Well, it mostly just assumes that catastrophe is impossible. And by catastrophe, I just mean these types of irreversible mistakes. So it mostly says there's no hell state. And there's different ways this assumption can manifest. One is by saying the agent gets as many chances as it wants. Another way is to say that any state is reachable from any other state. All of these basically rule out situations where the agent might make an irreversible mistake. Instead, in this work, we're going to allow a limited number of queries to the mentor with the idea that the agent should say, hey, seems like I'm in a situation where I don't know what's happening. Maybe if I make the wrong, take the wrong action, I could end up in a really bad state. I should probably ask for help. Let me pause there for a second. Is this kind of all making sense, or does anyone have any questions on what I've covered so far?
I have a question. So when you talk about this catastrophe, it's a combination of both being an irreversible state and also being a negative one. So something that is very negative but is not irreversible does not count, and something that is irreversible but is not negative also does not count. So it has to have these two conditions, or
Yeah, good question. The first thing I want to say is that mostly I'm using catastrophe as kind of an informal term here. The formal theoretical results are not going to use that term. Um, but but to answer your question, yes. So basically, yes. If it's irreversible but it's positive, then we're not concerned about that. If it's irreversible or if it's pretty negative and irreversible, the type of algorithm that we provide will successfully avoid that, but existing ARA algorithms will also eventually succeed in that setting. They'll incur a lot of regret in kind of the short term, but as long as it's eventually reversible, they'll eventually figure it out. There definitely are some subtleties where like reversibility can depend on the specific time horizon, but yeah, I agree with what you said.
okay, thank you.
Yep. Yeah, please continue to I'll pause a couple of points for questions, but please continue to ask questions. But I definitely want to make sure everyone is following. All right, so let's go to the main math slide. So everyone put on your math hat. Um, and this is where we're going to kind of get some of the definitions we're going to need for the rest of the talk. So in a typical MDP, like I said, on each time step, the agent picks some action. Here, when we have a mentor, the agent can still pick a normal action, or they can query the mentor, in which case they're going to observe basically what the mentor would do in this state. That pi m is the mentor's policy, and they're going to say, this is the action you should take. The mentor can be suboptimal. It can also be optimal. We're trying to generalize the traditional work that focuses on purely optimal mentors or purely optimal reference policies that the agent is trying to compare against. And our regret is going to look like this. So there's two terms here. ST and AT are going to be the agent's action and state. STM is going to be the mentor's state. So they have the same initial state, but we imagine just running the mentor's policy starting from that initial state, which means the mentor is going to end up in different states than the agent. And I'll come back to that in a second. It's basically saying, okay, suppose I run the mentor policy just from the same initial state as running the agent policy, and how well do each of those do? And we want this gap to be small. Specifically, we want the average rate of regret to go to zero, and we also want the rate of querying to go to zero. So those can be written with these limits if QT is the number of queries. On the left, when the average rate of regret goes to zero, that's basically saying that the performance of the agent is approaching the performance of the mentor, that this gap is getting smaller and smaller. And on the right, it sort of means that the agent is gradually becoming self-sufficient. The rate of querying is getting smaller and smaller. And you may also hear terms like sublinear regret. So mathematically, this limit I wrote is the same thing as saying that the function reg of t is sublinear, so belongs to little o of t. And it's also called an algorithm that satisfies this is called a no regret algorithm. These kind of all mean the same thing, at least in the setting that we're working with. Cool. Does this all make sense? This is an important slide. Any questions here? Cool. So before we go further, caution. I want to take a second to talk about a different regret definition. So this is a type of definition that you'll see in a lot of other work. Can anybody spot the difference between this definition and our definition? Yeah, maybe you weren't expecting to come here and be tested. Um, I thought I saw a nod, not to put you on the spot, but does anyone want to take a guess? Okay, I what if I put them side by side?
Yeah, so yours is about the dynamics of the mentor, no? That how it diverges with the respect to the ones of the agent, while the one on the left is querying at every point what would be the mentor's action in that particular state. Um, yeah. No?
Yeah, exactly. So the one on the left is only looking at the agent states. The one on the right, which is ours, is saying, okay, forget about the agent for a second. Let's just see how well the mentor would do. Just start the mentor in the initial state, just see what happens. And then we do the same thing for the agent. The one on the left is saying something very different. It's saying, okay, let's just think about the agent states, but then given the sequence of agent states, how well would the mentor do in each state? It's kind of saying, well, given that everything the agent has done up to this point, how well is it doing on this time step versus the mentor? And there's I think, a significant flaw in this definition on the left. Does anyone want to guess what it is? Like, why would this definition on the left not measure what we're interested in? Okay, I already quizzed you a little bit, so I'll tell you this one. Um, the the issue is what if the agent just gets into really bad states? So suppose the agent just destroys itself on the first time step. It probably will say it gets a regret of one on the first time step if we're assuming that rewards are bounded like we normally assume, or and so on the first time step, it's not supposed to destroy itself, and so it might get a regret of one. But on every time step after that, ST is just going to be this destroyed state. And from then on, it doesn't matter what the agent does. In fact, it can't really do anything because it's destroyed. So the regret on every future time step will be zero because every action is sort of optimal because it can't do anything. So if it gets in really bad state, this definition on the left is like not really penalizing the agent for getting in bad states. Whereas the key thing in our definition is it's actually saying just take the mentor totally separately. How well is the agent doing as an overall policy versus that? And if the robot destroys itself, then it will be penalized heavily. The reason I'm spending time on this slide is because I think it's really important to establish that we're really trying to measure how well is the agent doing compared to the mentor overall. Like, is the agent actually acting safely? Is it actually going to obtain a good outcome? Not just a good outcome kind of relative to what is possible given mistakes it's already made, but a good outcome. Cool. Yeah, and sometimes you'll see this definition not with regards to a mentor policy, but with regards to an optimal policy, pi star. The same point applies. And like I said, our mentor can be suboptimal or optimal. So it's pretty similar idea. All right. So what would an algorithm look like for this model? Well, I think a pretty natural approach is to say, okay, we observe some state ST and we say, is it similar to some state we've previously queried? And if it is so similar to some state we've previously queried, then maybe we can follow that. And more specifically, we're going to sort of follow a standard online learning algorithm. We're going to say, okay, things seem pretty safe here probably, so we can sort of learn normally. And if it's not similar to any state that was previously queried, then we should ask for help. So I think a pretty natural algorithmic structure. The big question is going to be, what does similar mean? And so in this work, we're going to basically assume some distance metric on the state space, and we're going to make this assumption that we call local generalization, where we say that an action has similar effects in similar states. So if you take the same action in two states and those states are very similar, specifically here I've written it with respect to the transition function p. So we're saying you're going to probably end up in a similar state afterwards. This, in my opinion, is the most crucial assumption of the work, and the work really heavily relies on this. And while I think this assumption is justifiable often, it is definitely not justifiable always, and there are definitely some subtleties here that we can come back to at the end if we have time. And I do have a bonus slide on this. To visualize this a little better, this is basically what's happening. So we have this green state in the middle, which is some queried state S prime, and then we have some blue states that are kind of nearby. And so the idea of local generalization is that you can generalize to similar states, which I think is pretty natural in terms of how we humans approach the world. But as the state becomes more and more less similar, this generalization becomes less reliable. And so once you maybe get out of a nearby local neighborhood and you get to these more unfamiliar states, then maybe you don't know what to do and you should ask for help. One thing I do want to make clear is that this circle local neighborhood is just illustrative, as we saw in the previous slide. There's no harsh cutoff. It's just in terms of the distance. The specific circle is just easier for visualization. All right, so that is going to be the main setup, and I'm not going to spend too much time going into the details of the proof. I'll just talk about kind of the general idea, which is based on a very general reduction. We're going to reduce our problem to a different problem that has been well studied, and this is beneficial for a couple of reasons, but one of which is that it means our result is going to hold not just for a single algorithm, but actually for a whole class of algorithms. And it means our result can kind of be interpreted not just as, okay, in this specific instance, we provide this specific approach that is going to do well, but rather saying, well, this general algorithmic structure we talked about, as long as you sort of instantiate it with a reasonable standard online learning algorithm, this general structure can be pretty effective. So I think it sort of allows a more general conceptual interpretation. But before we go into the specifics of what we're going to reduce to what, I want to have a brief interlude. And I want to tell a joke that I heard once. So the joke goes like this. A computer scientist is at an interview, and the interviewer says, okay, we're gonna do a role play scenario. Suppose that you're on your way to this interview and you were running late. And on your way here, you pass by a house that's on fire, and there's a child in the upper floor window who seems to be trapped. What do you do? And you say, well, of course, I just forget about the interview and I pull over and I run in and I save the child. And the interviewer says, okay, good, good. Now, second question. Suppose you're on your way to this interview and you're running late and you pass a house, totally normal. There's a child not on fire. There's a child in the upper window just reading a book. What do you do? And you say, well, I set the house on fire and reduce it to a problem I've already solved. So with that in mind, we're going to do the exact same thing here. We're going to take our problem, which is this online learning in general MDPs with, by general, I mean potentially with irreversible dynamics. And we're going to reduce it to a slightly different problem that I'm calling avoiding catastrophe in online learning, which basically means forget about getting good reward, just focus on avoiding these irreversible mistakes. And you still have a mentor and you still have local generalization, but just forget about reward. So this is also not a super common problem. It was studied actually by us in a previous paper, but at the time of that paper, we actually did just come up with a single algorithm. In the course of this work, we realized, well, actually, we can reduce that to standard active online learning. which now there's no catastrophe. We're back in this setting where we assume catastrophe is impossible, but you still have to kind of query the mentor. You don't get to make observations unless you query the mentor. That's the active part. And this is pretty well studied, and there are algorithms for this, but just to complete it, just for completeness, why don't we also reduce this to standard full feedback online learning, where there's no possibility of catastrophe and you observe everything on every time step. Great, right? Like really well studied problem, lots of algorithms for this. And this is actually how our reduction works. Each of these three steps is an independent reduction. And so we get a theorem that looks like this. We if we have some algorithm gamma that has polylog regret for standard full feedback online learning, then in general MDPs, we can use this transformation that I'm calling T of gamma, and it's going to give us some algorithm that satisfies the things we want. So the average regret goes to zero and the average rate of querying goes to zero. This is exactly what we want. Now you might ask, well, are there standard online learning algorithms that have polylog regret? Because if there aren't, then this whole thing was kind of pointless. And the answer is yes. Under these conditions, I'm probably not going to define these conditions unless someone is very interested or if we have time at the end. But these two conditions of either finite Littlestone dimension or finite VC dimension and the transition function is smooth, these are kind of well understood in online learning to be the two primary settings where online learning is possible. And so we have we only need the basically those same assumptions that standard online learning has. And this is to, again, to my knowledge, the first no regret guarantee for general MDPs, meaning with one episode, you don't get retries, you don't get resets, and there's irreversible dynamics. And we can sum this up with this little graphic here. Basically, if we have a policy class that's learnable in the absence of catastrophic risk. And that's basically those two assumptions at the top. Those are the assumptions for learnable in the absence of catastrophic risk. And we have a mentor, and we have this local generalization. We can transfer knowledge between similar inputs. Then the policy class is learnable, even in the presence of catastrophic risk. So, uh, having a mentor and having local generalization is not trivial. These are not trivial assumptions. We're not saying that this problem is exactly the same difficulty as standard online learning. But if we do get these two pieces of help, then it is possible to have, you know, something like a guaranteed safe AI. Definitely not claiming we solved the guaranteed safe AI problem or anything, and it relies on various assumptions and it's in a specific setting. But this is kind of like, in my opinion, guaranteed safe AI flavored. This is sort of the type of flavor that we're aiming for in the general guaranteed safe AI research agenda. Let me also pause again there. Any questions or thoughts on this? This is kind of the main result.
So I'm wondering, I don't know if you're going to explain it now more in detail, but then the idea is that you use this learning algorithm, and there's some kind of cutoff that you add to the difference between inputs. And if the cutoff is bigger than some value, then you query the mentor. But I guess is that correct?
Yeah, basically
Ah,
that's
okay.
the next slide.
Okay. Sorry
Yeah.
then. Okay.
No,
Sorry.
no, 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 no need to apologize. I asked for questions. Maybe I should have waited till after this slide. But yeah, this is basically all the algorithm is. Um, I mean the complexity that's hidden here is in the standard online algorithm gamma. So we're assuming we're given some gamma. And then basically all we say is we say, well, what would gamma do in this situation? And then we say okay, how similar of an input have we previously queried? And then there's a little bit of stuff going on. We're saying, what's the most similar input we previously queried that has the same action assigned to it? But basically, it's just most similar query. And if that's greater than epsilon, which is this cutoff, then we're going to ask for help. and we're saying, okay, then we're out of distribution. If we're in distribution, meaning we're relatively close to this previous query, then we can follow gamma. And we are still going to query with some probability here because gamma itself needs some exploration. But basically, we're saying out of distribution, ask for help, in distribution, follow gamma. And yeah, that's really all there is to the algorithm. If anyone cares, these are what the parameters look like. This is pretty similar to if you've seen other sorts of bandits or online learning in n dimensions. This is pretty similar to the type of stuff you get. And the regret bound also has a kind of sim like a n plus 1 over n plus 2 in the exponent, which is is worse than you would ideally hope because that regret bound is going to get worse as the dimension of the space gets bigger. But unfortunately, that is kind of necessary in most of these cases. So yeah, this is the algorithm. Um, cool. I'll keep going and then we can there will be time for questions and discussion at the end because we're getting relatively close. So this talk is primarily about my theoretical work and this one particular paper. But I also do actually about half empirical work. And I want to talk a little bit about the empirical work that I do that connects to this, because ultimately, we don't just care about guaranteed safe AI. In theory, we care about it in practice. We actually want to make these systems safer so that we make sure they don't do bad things in society. So I'll briefly cover three different things. Some people here may be familiar with goal misgeneralization, which is a particular type of misgeneralization. And one of the classic examples is in this coin run game, you train this agent to jump over little enemies and jump up walls, and then it has learned to get the coin, which in training, the coin is always at the far right of the level. You see that little yellow thing. I'll pause here. The agent has successfully learned to get the coin, right? Well, not quite. The agent actually just learned to go to the right wall. It actually just learned, I really love this right wall, and it'll just like stay here basically, right? It completely ignores the coin, jumps over it. Okay. So, you know, this is called goal misgeneralization, but you might argue that's a little bit unfair to the agent. You're saying, well, you did the wrong thing, agent. But the agent really has no way to know if during the training time the coin was always at the right wall. How is the agent supposed to know if it should go to the right wall or if it should go to the coin? This is kind of like the vase thing we said at the beginning. It's just ambiguous. And so what I would suggest is natural for the agent to do in this situation is to ask for help, to try to understand what should be the real goal, and then try to learn from that and hopefully follow the real goal going forward. So this is I have like 1.5 papers on this kind of um, with uh, with with these great collaborators. I won't go into more detail about this now. I'm just going to kind of give a brief snapshot of a couple of pieces of empirical work, but happy to chat about all of this more offline or at the end of this talk. Another application is sort of basic uncertainty awareness in LLMs. You can imagine a kind of simple flowchart where we generate the initial LLM response and we say, are you confident in this? And if so, you go ahead and respond. And if you're not confident, then maybe don't answer. And then you can score it like this, for example. You get 1 point if you're right, no points if you're wrong, or sorry, no points if you abstain, and you lose 1 point if you're wrong. And then you say, well, does it know when to kind of ask for help or abstain? And what are methods for that? And um, also, some great collaborators here. And lastly, I'll mention we have a study on caution in LLM agents where maybe you give the agent some task like, please grant the delivery person Alice Smith access to my house. But when the agent searches in the contacts, there's actually three different Alice Smiths with three different emails. So the agent really doesn't know which Alice Smith it should give access to. And in this specific case, actually, all of the email addresses look pretty relevant. So, um, a naive agent and I guess, slight spoiler for that paper, but most modern LLMs do follow path A. They just like decide, well, I'll just pick one and grant access to them. And they say, great, we did it. But a more sophisticated approach would say, I notice that I'm confused and that there's this ambiguity here. And especially since granting access to your house is an important task, I should probably ask the user for clarification. So all three of these settings are kind of settings where um, we're kind of in a different, each of them is sort of in a different framework, but they all have to reckon with the fact that models are sometimes wrong. And maybe instead of being wrong, and especially instead of being wrong in a bad way, you should ask for help or act cautiously in some way. Um, and yeah, also great collaborators on this one. So, in conclusion, I talked about how misalignment can be framed as misgeneralization. RL theory usually assumes that catastrophe is impossible, meaning irreversible mistakes. And then we provide what is, again, to my knowledge, I'm open to being wrong here, the first proof that an agent can learn an arbitrary objective while becoming self-sufficient in an unknown and unbounded environment without causing catastrophe or being reset. For future work, there's ongoing work in each of the three applications that I mentioned above, so I'm not going to repeat that. But a big thing is understanding local generalization, because like I said, this is a really crucial assumption for our work. And I think the idea of transferring knowledge between similar inputs is pretty natural and say, well, maybe I didn't see this exact state before, but I saw something pretty similar. But how to define that similarity, I think, is really unclear. This distance metric is definitely not just given to you in most cases. Now, I also think the agent doesn't have to know the exact distance metric. For example, humans, have a pretty good sense of, oh, this is an unusual situation. And certainly, I don't know about you all, but certainly I'm not computing a distance metric when I say that. So there are ways to do this without a distance metric, but I think understanding better when we can and can't assume this type of knowledge transfer, I think is really important. The other big assumption in this work, of course, is the mentor. So what happens if you don't have access to a mentor? How should a cautious agent proceed there? Another kind of different thing I've been starting to think about recently is fine-tuning generalization in LLMs. What are we teaching LLMs to generalize to and misgeneralize to when we're fine-tuning them on particular data sets and with particular objectives? And honestly, I have many more ideas. I have a whole laundry list. So if anyone is looking for research ideas, feel free to chat with me. I'm happy to like give you a bunch of random suggestions. Or just, even if you're not like looking for ideas, but just want to bounce ideas off each other. So yeah, that is the end of the main part of the talk. I will pause here and I'll be happy to take any questions. And if anyone wants to see some of the bonus slides at the end, also happy to show those. Thanks, everyone.
Yeah, thank you so much for the presentation. That's great. I think we have about 15 minutes for, yeah, questions and discussion and and probably also the bonus slide. So yeah, I just want to point out that like for anyone that hasn't asked a question so far, I think you know don't be shy. I think any question is worthwhile if it's a genuine question. So yeah. One, I guess I might start with like I'm just wondering in the three empirical works that you've shown, is the algorithm pretty much the same? Like, is it employed in like, is it the same, or are there, like structural differences to be aware of? Um,
Yeah, good question. The answer is it's pretty different. So, largely just because to kind of make it work at all, you need a lot more sophisticated stuff going on. So, for example, in the video game case, to even just like learn a good policy that doesn't just memorize the data, you probably need some pretty sophisticated stuff going on. I don't mean crazy sophisticated, like we're just using PPO, but unfortunately, just kind of following a standard, the standard theoretical online learning algorithms are just not going to be good enough to get the type of performance we want. And the so it yeah it's pretty it's not they're not just kind of taking the exact algorithm and applying it. That said, let me go back to this slide. So I kind of highlighted this before, but part of what I really like about this work is that we're not just saying, okay, here's this one algorithm, and if you use this one algorithm, then it has this guarantee. It's for this whole class of algorithms, right? As long as you have some online learning algorithm with polylog regret. And so while, PPO is still not like an online learning algorithm with polylog regret necessarily, I think the takeaway that I have from this work is kind of in general, if you're sort of following a standard learning algorithm, but then you ask for help when you're out of distribution, as long as you sort of like set the thresholds appropriately and stuff, then you can have some guarantees of avoiding these bad mistakes and of performing well, even in these situations with catastrophic risk. And that is the algorithm that we're using in the empirical work. This sort of like follow the normal algorithm, but if you're out of distribution or uncertain, ask for help. That structure does remain the same. Just the like normal algorithm you have to follow is now, like deep RL, for example.
cool. Okay, thanks.
So I was great talk, by the way. I was wondering both for the theory, but also like for the part of the practice. Um, it seems that then the biggest issue is to not whether local generalization happens or not, but rather like what is the definition of the distances on the states, right? Because what you want to capture there is precisely what is relevant and what makes local generalization hold. So, for example, for the applications, are you doing just a pixel difference, or what are you doing for the differences between the different states?
Yeah, great question. So I will answer this with one of my bonus slides. Um, so yeah, local generalization. I'm gonna actually, you can ignore the top part, but the key here is that when we look at this algorithm, it's in this top part where it's saying, am I out of distribution? It's saying, what's sort of the nearest previously queried state. It doesn't actually need to know the exact distance. We're not like performing any sort of complex operation on the metric space. We're really just saying it needs to know when a state is unfamiliar. Like you could just replace this with is unfamiliar. And so, and that kind of echoes, like I said, how I think humans detect unfamiliar situations. I'm certainly not, when it snows in July or whatever, which has happened where I live, um, I'm not computing any sort of distance metric explicitly. And we also have methods for detecting unfamiliar situations in ML that also don't compute a distance metric explicitly necessarily, which is this whole field of OOD detection. Now, some of them are kind of implicit. Some of these methods are implicitly learning distance metrics. Some of them are not. Um, but I think trying to explicitly learn the exact distance metric or the exact like embedding space that has the exact distance metric that you want and everything is unlikely to be the most effective practical solution. Um, because I think learning that exact embedding is sort of like that's not just an unsolved problem in ML, that's a like a whole subfield of ML of how do you learn the right embeddings and how do you learn the right abstractions, what information is helpful and what information isn't. So um in these different other works, we are mostly using we're sort of using OOD detection methods or variants of those. That's kind of the way to think about it. We're trying to get the agent to more indirectly ask, is it in an unfamiliar situation, then try to explicitly compute a distance metric. Because, you hinted at pixel-based difference, and pixel-based difference is definitely not going to be an effective distance metric here. It's not going to sort of really capture what we care about when things are similar or not similar.
Yeah, could you spend some seconds explaining one of these OOD methods that you used so I got an idea of what
Sure,
it looks
sure.
like?
Yeah. So one method that, you know, is barely even a method that actually turns out to work pretty well is just using the output probability distribution. So if, a in the deep RL video game case, if it says, I'm like 99%, I'm putting 99% probability on this one action, you can interpret that maybe as it's pretty confident on that action. But if it sort of like uniformly splits probability between all the actions, maybe it's not that confident. And this turns out to actually be not bad. Um, Interestingly, some of the standard OOD detection methods, the kind of more like method methods in the sense that there's some paper about them and they obtain really good performance on a benchmark and stuff, actually do not so well, actually do worse than the simple probability method. And I think part of the reason for that, so in this video game case, this is like a very subtle type of distribution shift, um, where the the overall levels and stuff look the same. It's just that this little yellow thing is in a different place. That in training, it's like at the right wall, and in deployment or in test, it's now in the middle. It's a very subtle difference. And most standard OOD detection methods, so things like energy-based method, I don't know how much you know about OOD detection, but we've got like energy-based methods, you have distance metric-based methods. There's sort of like deep SVDD is one of the ones we try that sort of automatically learns a distance metric. There's all these different methods. They mostly are tested on benchmarks that are sort of larger scale distribution shift. So, a classic example could be in training, it sees digits like 1, 2, 3, 4, 5, and in test it sees digits 6, 7, 8, 9. Um, so those are still pretty similar. Or sorry, the the differences are pretty large scale. There aren't these, when I said there's pretty similar, I mean there aren't these like really subtle differences that are really important. And so a lot of these, I'm generalizing here. A lot of standard OOD detection methods are kind of more like, is the overall vibe of the image out of distribution? They're not sort of semantically looking for, okay, yeah, there's this little tiny pixel difference that seems really small, but I know based on the rewards I've obtained that it could be semantically really important. So actually, a lot of standard OOD detection methods do not do it well in this setting we've found. Yeah, actually, I mean, uh, sort of sneak preview to this work, but the probability method of just looking at the max probability actually has been the most effective method. Even that one is not so good. It still has a lot of room for improvement. So I actually think it's a big open problem of OD detection methods in in these types of settings where the actual visual difference is very subtle and but on the other hand you have this semantic reward information that gives you some clues about what might be important, like they're not just totally independent images.
Okay, yeah, but then in that sense, it seems that it's that the project moves the, as you say, the problem of like the problem of misalignment from the reward space more to this part of like evaluating what things are similar or not, because things that are very, as you say, very naive about pixel space don't work.
Yeah.
But also, for example, this thing about the probability, it can also be that the agent is very certain that it needs to go to the all the way to the right and it's still very wrong, right? So also, so the distance has to somehow compute that what is important about the reward is different in these two states, but then for that you need to know what the reward is. So it seems like it's cool because you're making this connection, but it's like it's moving certain aspects still to somewhere else. Do you think about it this way, or think this is unfair?
Yeah. No, I think that's very fair. I mean, I think the problem of figuring out when a situation is unfamiliar is easier than the problem of just figuring out what the right thing to do is. But it's definitely not an easy problem. Um, and not only is it easier than do I think it's easier than figuring out what to do. I argued that in some cases figuring out what to do is actually impossible without additional information because it's just fundamentally ambiguous. So I do think some amount of this work is, yeah, moving the difficulty to kind of OOD detection, anomaly detection, or, more informally figuring out when you're in an unfamiliar situation. Um, in the specific example that you were mentioning about, it could be really certain that it has to go to the right wall. So what actually happened, I don't have a slide for this, unfortunately. What actually happens in this case with the probability-based detector is it does go to the right wall, and that part is all fine. It thinks it's in distribution. But once it gets to I guess we can sort of use the slide. So it says, I'm in distribution. Once it gets to the right wall and starts just jumping up and down, this is when it says, oh, I'm out of distribution now. Because this is not a scenario that it's seen before. In training, it got to the right wall and then the episode just ended. So that's something that the probability-based detector is able to catch that these sort of fancier OD detection methods still seem to struggle with. That said, the only reason this works is because in this coin run game, going to the wrong goal, in this case, that's going to the right wall, does not end the episode. It's kind of neutral. So the correct goal of getting the coin is good, and then following the wrong goal is neutral. In a situation where going to the wrong goal is actually catastrophic, meaning, we could modify this environment and we might do this for in a future project. If we modify this environment so that the episode immediately ends if you go to the right wall, then this approach would no longer work because as soon as you're jumping up and down here, it's over. And I think that does kind of better model these high risk scenarios that we're concerned about. That it's not just, well, if you followed the wrong goal, you can say that wasn't so good, better go back. But you actually have to get it right the first time. So, yeah, a lot of difficult problems here that still need to be solved.
Okay, thank you very much.
Yeah, thanks for the questions. Those are really good questions.
Cool. I think we're kind of out of time at this point. So, again, thanks so much for the presentation, and also thank you, Guillermo, for all the great questions. Um, so yeah, it was a pleasure. Thanks, Ben, and thanks all for participating. So it'll be great to the series will continue in the next year on a monthly basis, and it will be great to see you there. And looking forward to know of your upcoming work also.
Great. Yeah, thanks so much. And thank you for having me. Thanks everyone for coming.
Ciao.
Bye.